Alright, Team Fun, welcome back to more online distance learning calculus. We're up to day 94, and this is our third to last day of new stuff for the entire year. After 94, 95, after day 96, we just have review and then get your AP exam where you're all going to earn college credit, and that's that. So let's get to it. I'm going to again split this video into two pieces. The first piece is going to take you through the assignment check, which you should of course do on your own. You have 10 minutes for it, and two example problems. The second video is going to take you through some practice problems. So let's get started. You have an assignment check. It is calculator active. You will need your calculator on this. There are two problems, A and B. You should try to do this without your notes, and it should be pretty fresh in your mind because you just learned it yesterday or the day before. So go ahead, pause this video, take 10 minutes, try the two problems down below, and then at the end of the 10 minutes, come back and I'll show you how to do them. Ready, set, go. All right. So you've already done the assignment check. So because it's calculator active, I skipped a couple steps to try to save some time here. I went ahead and graphed each of these functions. I have this first function, which I called f of x equals the natural log of x. And I also have the second function over here, which is going to be g of x equals 5 minus x. Nothing too terrible. I've graphed those on my calculator already, and then I'm pretty sure we're going to need the intersection point of the two. So we're going to go to Menu, Analyze Graph, Intersection, and I'm going to try to do okay with this. I think I'm doing all right so far. Excellent. Then I'm going to drag this intersection over here. Don't forget, we'll need more decimals than that, but to save us some time, what we're really just going to do is we are going to store each of these. So I'm going to store the first one as A, and then I bet I'll need the Y as well. So I'm going to go ahead and store the second one as B. A and B, very creative like all mathematicians. Just to double check, 3.69 if I type in A over here. Oh, 3.69. Phew. Okay, I'm on the right track so far. Already better than last time. So let's get to it. For each cross-section perpendicular to the x-axis, we want there to be squares. All right, well, I'm able to erase on this. You guys might have a little bit of a harder time here, but I'm going to go ahead and get this started. So here is my square. It looks something like this over here. Look at that square. That was pretty good. I'm proud of myself. We've got a base and a height. Okay, now the problem though is that we want the volume of this solid, and I see two different squares here. I'll do them in two colors. We've got one square that's right here, but then we have a second square that's over here. And the reason I say two different squares is that the first square in blue is created by the red function minus 0. So I'm actually going to split this into two pieces here. I think I can probably do this with enough space. So first thing I like to do is write the area function for this square. My area function is going to be the base, which is natural log of x minus 0. Okay, which I'm just going to write as natural log of x times the height, but because it's a square, the base and the height are the same, so it's natural log of x squared. Easy enough. All right, maybe I'll call this a sub 1 of x. And then I have a second area function with the purple one over here. My second area function is again going to be the top function minus the bottom. The top function is 5 minus x, the bottom function is 0, and the height is the same thing, so there's my second area function. Of course, area is not good enough. We need volume here, so I'm going to go ahead and give this a little bit of width. We can see this width is along the x-axis. That's dx here. Same thing over here. We're going to give you, oops, it's supposed to be purple. I pressed purple. And we're going to give this one a little bit of width as well. That's looking okay. And with this width here then, we have another dx along the x-axis. So let's get our volume functions. My first volume function is again going to be my natural log of x squared, but to give it that third dimension we need to multiply by dx. And same thing over here. V sub 2 of x is going to be 5 minus x squared, but the width is dx. Okay, we're doing all right. But then we need to remember that we have a lot of these squares, right? There's going to be another square over here and another one over here, and they're all going to get added up together. We need to add up all of these different volumes. So to add them up, we need to involve our integral. We're going to integrate here the 1 three-dimensional rectangle, but then we need to sum it up. So where x is all the way through, so we're starting at 1, and we're going over to, oh, what x value here? Well, we found the x value is 3.69344, and to save us some time, we might even just want to write the point up here, and we'll say we're going to let a equal 3. I've already forgotten, I think it was 69344, 693 dot dot dot, and we're also going to let b equal, and what was b? Let's just type it out. It's probably easier than me trying to navigate this calculator. Variables not defined. You're lying to me. I totally saved that as b. Maybe I hit a different letter. So control store b, enter. Ha! What now? Now I can hit b, and we've got it, 1.306. So we have this 1.306 dot dot dot. And again, by showing what a and b are, now I don't have to write these out. So I'm going to integrate or sum up all of my blue squares from 1 to a. And then I'm also going to need to integrate all of my purple squares from what to what? Well, definitely starting at a and ending up over here. 1, 2, 3, 4, 5. 5 makes sense. 5 minus 5 is 0. A to 5. And they wanted the total volume. Well, let's just get real lazy here and put a plus in between. We're going to add up all the volumes, and I think we're done. All right. Well, what does B ask? B says, okay, same thing, but now our cross sections are perpendicular to the y-axis. Oh, okay, so this time we're going the other direction. So other direction means, and I'll try to draw a nice little picture here as well, that we're going to go side to side here. And in addition to that, we also need, let's use yellow, we need to make sure that our cross section is a rectangle whose height is twice the length of its base. So if it's twice the length of its base, that means that the base is the short part. And here is my, ooh, that's going to be way too big. So here's this. It's going to be something like this. That sounds all right. Sure. There is my rectangle where we have our base and we have twice the base for the height right here. It's not my best work of art, but it'll pass. So let's get to it. My area function of this, well, area is base times height, so we have base times height here. The base is the distance between these two functions. Now we're going right and left here. We always want to do the right function minus the left because x values are bigger on the right than the left. But in order to do that, each of our functions need to be solved for x. So y equals 5 minus x. We're going to add x and subtract y. I'm getting x equals 5 minus y. And for my function over here, we originally had y equals, I don't want to do that there. We originally had y equals the natural log of x. We exponentiate each side, e to the power of each side. That's going to give us e equals x to the y, or x equals e to the y. So right function, 5 minus x. And the left function is e to the y. And that will give us our base. Well, how is our height different than the base? Well, it's exactly the same, except it's double the base. So 2 times 5 minus x minus, and then e to the y. Now, I wrote in 5 minus x twice because apparently my brain is on crazy pills. So let's try this again. It should, of course, be 5 minus y. And I instantly realized that when I looked at e to the y and realized, wait, I'm using y's, but I wrote an x. So let's simplify this down slightly. And I think this is just going to become, let's move the 2 out front, 5 minus y minus e to the y squared. There's my area function. Okay, let's give it a little bit of width here. We're going to kind of jump up this way, come over this way, give it a nice little rectangular width, nothing too bad. And of course that width, my volume formula, is 5 minus y minus e to the y squared times dy. Looking good so far. And then last but not least, we need to write an integral that gives us the volume of all of these rectangles coming over here, because of course we have many of these rectangles being summed up. So let's get to it. Integral, we have this 5 minus y minus e to the y squared dy from where to where? Well, everything's in terms of y. So I'm going to put y equals just so I don't forget. The lowest y value down here is the y value of 0. This is the point 1 comma 0, 5 comma 0, so it's a y of 0. The highest y value, well, that's b up at the top. So 0, to be. And we're done. Some people have emailed saying, do I have to show all this work? No. On this problem, they're just asking for the setup, and you can just show this. However, you do need to show what the intersection is somehow. You can show you set them equal to each other and then found it. You can just draw an arrow to point, anything like that, but make sure you show what the intersection is. And that's your assignment check. All right, now, good news. Today is not really anything new. We only have 2 example problems and you're done with this video. Today is just taking what we've already done and adding extra shapes. So here we go. Using the base from last class, I'm already drawing the base. It's just been drilled into my brain. We had y equals ln of x, which crossed at 1, 0. And then we had the line x equals e, which is 2.7 something. That's right about here. And then we had y equals 0, which is the x-axis. So we have our base, which looks something like this. And then it came in handy last time, but I needed this point. This was the point e, 1. So my region that we're looking at is this region right here. What are we doing with it? 3-dimensional shape, yada yada, is created by semicircles that are perpendicular to the base and the x-axis. Oh, drawing these every year, I always laugh. I always mean them to look like semicircles, or you can think like this beautiful arching bridge, and without fail, mine always look like tacos. But either way, here we go. So we need to draw a semicircle that is bridging between the base and the x-axis. So here is my piece right here, and here is my semicircle that's coming off the page at you. It's a little bit tricky to see so far, but either way, that's my semicircle. So just to redraw it really quickly, here is the semicircle. All right, this is a little bit trickier. So let's just start with how we know to find the area of a semicircle. An area of a full circle is pi times the radius squared. The area of a semicircle is half of pi r squared. So let's try to write our area function. Area function's a little bit more challenging. That's why we saved this for today. Well, the area is going to be 1/2 times pi times the radius. Well, think about what this piece is down here. This piece is not the radius. This whole piece is the diameter. So let's at least start with the diameter. The diameter here is found by doing the top function, which is natural log of x, minus the bottom function, which is 0. Okay, that's not too bad, but how do we find a radius? Well, a radius is of course half of a diameter. Maybe I'll show that in green right here. This is my radius. Ooh, picked a poor color there. That's all right. We can make it work. This is the radius, and it's going to be half of the diameter, which means half of the natural log of x minus 0. Or some people will even write that as natural log of x minus 0 over 2. That's pretty common. So actually, that's what I'm going to do. So 1/2 pi, my radius is natural log of x minus 0 over 2. And yes, you can skip the minus 0. Right now, though, this would just be one-dimensional. If it was 1/2 pi, that's a constant, times a single radius, that'd be a one-dimensional shape. But a circle or a semicircle is one-dimensional. We need to make it two-dimensional by giving it a square. There are 2 radii multiplying. So there's my area function. Ready for the taco? All right, we need to find our volume function. Our volume function is going to be 1/2 times pi times the natural log of x over 2 squared times dx. We need to give this semicircle a little bit of width. And to give it a little bit of width comes, oops, that was even worse than normal. It's going to, losing pieces everywhere. Okay, undo. There we go. Third tries the charm. Okay, so it's going to come over here and drop down. And now we have my little bit of width, and as soon as I put these in, hopefully you're thinking, that's not a little bit of width, that's a taco, and it is. So there is this semicircle coming off the page at you, and we've now given it this width right here, which is our dx. Last but not least, we need an integral to sum up an infinite number of semicircles. So we integrate, and before I integrate, I'm going to clean this up a little bit too. I'm actually going to do this twice, I think. So we're going to do the integral, 1/2 times pi. I'm going to distribute the square here. That becomes the natural log of x squared over 2 squared, which is 4 dx. And what am I summing up all these semicircles from? Well, we start at 1, we end at e, so 1 to e, and we're looking pretty good. That's really it. However, I'm going to simplify a little further just so you could see what this might look like on a multiple choice question, or how you could simplify and save yourself some time. So we have 1/2 times 1/4 that's right here. That's going to be 1/8. 1/8 is a constant, so I'm going to write that outside the integral. And the pi is also a constant, so I'm also going to put that outside the integral. So that just leaves me inside then 1 to e natural log of x squared dx. And that's a nice little bit more succinct way to write our final formula. Okay, we have one more problem and you're done with this video, and then you're moving on to the practice and then the second video if you need it. So, last one. Same base again. Yes, we're crushing this. We're getting really good at drawing natural log, drawing x equals e, drawing actual parallel lines to an axis instead of weird curvy ones. Here is 1, 2, 3. X equals e, we did kind of right here before. Sounds lovely. We have our natural log, and it goes up here, and then we said that this point was the point 1 comma, nope, switch it around, e comma 1, and I think we're okay. Alrighty, find the volume three-dimensional shape whose height is created by an isosceles right triangle. What does it even look like? Well, an isosceles right triangle, let's start with a right triangle. A right triangle, of course, has a right angle. But that is not isosceles, because isosceles tells you something about the sides of any triangle. It tells you two of the sides are the same. Now, for an isosceles right triangle, we know the two sides that are the same have to be these two, which are called legs, because the hypotenuse always has to be the largest side. There can't be any other side that's the same as the hypotenuse. So this is our isosceles right triangle. So it's perpendicular to the x-axis, good so far, and it has a leg in the xy plane. Why are they telling us where the leg is? Well, otherwise, you could draw this triangle, and I'm going to redraw it down here, where, and this is going to be really tricky to see, where this right here is my hypotenuse, and then the two legs would meet up like this, and if you gave it some width, it'll look something like that, right? Kind of like a Dorito chip standing on its side. But that's not what they want you to do. They don't want the hypotenuse to be lying, and this whole thing is our xy plane, right? They don't want the hypotenuse there. What they want there is a leg. So instead, my triangle is going to look even trickier. It doesn't matter which way it goes here, but we're going to have a leg, we're going to have a second leg, and then this right here is going to be my hypotenuse. Here is my cute little right angle that looks like that. Yeah, so there is my triangle. And we know that in an isosceles right triangle, the legs are the same. So what are we trying to do here? Well, usual thing, we need an area function. My area function is, well, how do we find the area of any triangle? That's 1/2 of the base. Let's not do a of x yet. My area is just going to be 1/2 of the base times the height. Okay, or in this case, the legs are actually the same, aren't they? So we could even simplify that. It's 1/2 of the leg, right? That's like our base. But then the height is also the leg as well. So it's the leg times the leg, or if you want, it's 1/2 the leg squared. That's nice. So let's write our area function. Area, guess what? We're going to do 1/2. We need the leg and then a square. The leg is created by my top function, again, natural log of x, minus the bottom function, which is 0. And cleaning this up a little bit more, that just looks like 1/2 the natural log of x squared. Good so far. Alright, I think at this point we need our volume formula, and you know where this is going. We take our two-dimensional shape that has that square, and we give it a third dimension, which is some width. Okay, here is my third dimension, right? This is my dx right here, and this is got to drop down and come across. Okay, so there's my third dimension. And last but not least, we need to sum up a lot of these isosceles triangles. So we need to sum up 1/2 natural log of x squared dx, starting at 1, ending at e, and we are good. So, long story short, too late, name that movie. what you really need to do here is you need to set up your area function first. The area function, I think, is the most challenging part. You need to know areas of any shape. It could be a trapezoid, rectangle, square, semicircle, some sort of triangle. Get that area function set up. Once you have your area function, dx to become volume, and then sum up your volumes with an integral. Thanks for watching. At this point then, you have, let's see, 1, 2, 3, 4 problems to get through. This one will probably take you a little bit longer. If you get stuck on any of them, you can watch my other video, but if you feel confident, you should be good to go. I'm excited for you to turn this in on Teams and hopefully see your lovely faces next week.